Hello, everyone. I go by Zion Online, and I am trying to build the programming language to end all programming languages. Can everyone see what's in the
first one?
First one.
Are you also called Zion Sheep for the purposes of this video?
Yes.
Okay.
Basically, like, how do you make a language that can build all the other languages and transpile them all down to one? So what is a decentralized language, real quick? Basically, it's the idea where, like, you don't have a central Git repository for your language. Your language is basically a bunch of functions that people can, like, use to compile code and transpile code between various representations and type systems. And for that to be able to work, you need be able to prove stuff. But if you can prove stuff, you can, like, possibly maybe do this where you have a fully peer-to-peer language. There's no central repository, no like year-long RFC process. Yeah.
This isn't the language itself that does it. It's the language plus some supporting program you have that does this, right?
Could you elaborate on that?
So, I write an awk. Awk's a language. I don't have awk run itself. I use a binary program called awk to go ahead and, quote, interpret, compile, transpile, whatever you want to get the output that I want from the thing that I wrote in the language. So in addition to the language, awk, which is very nice for prototyping, I have a binary that helps me get the job done.
Mm-hmm.
So far you've talked about we've got a language which is decentralized. I don't understand why that is, but you're going to be able to use it to translate between existing languages. Don't you need a binary for that?
So one way you get around the binary problem is you re-implement awk in this language, the parser, the evaluator, the operations it does effectively.
Right. So I've got this lovely block of code that re-implements awk. What do I do with this lovely block of code?
Well, now you have awk as a kind of DSL in this language. Like you can make it so that you're writing in disp, and then you.
No, I'm not running yet. I have this lovely block of code. What do I do with it?
You can compile it or run it in an evaluator.
Something that compiles it. What is it that compiles it? I would call it a binary because I'm a dinosaur, but maybe there's a modern term for it.
Still on the second slide, you might be clear.
Okay.
I'll get to that later.
Thank you.
So basically, it is like you can't. You want to take awk, and you want to maybe have a simpler implementation, recreate awk in and its syntax. You use extend awk easily. You want to take the awk binary or the awk source code and, like, prove that it's equivalent to some other implementation that the AI generates. And the AI also generates the proof, and that for all possible input awk programs, for all the given output behavior will be the same provably. That's basically the TLDR behind this.
All right.
And maybe if we have this and we can, like, describe use type systems to describe arbitrary constraints, maybe we could, like, say, take this language model. It's a binary. It's like llama.cpp, and be like, hey, Fable 7, find me a symbolic program that is the smallest symbolic program you can find that perfectly re-implements this language model. That might be very useful.
Oh, do you have to use the phrase language model?
Well, in theory, it should be any possible program you can, like, encode in like some kind of representation.
But we're getting language model being used in another phrase, whereas if you have a language paradigm or a language paradise even, or something like that describes it, that would be good. But language model suggests a large language model or a natural language model. So I'm really hoping
precisely.
Come up with a different term.
That's what I'm saying. Like if you had a symbolic version of GPT,
yes,
you would solve the interpretability problem because you could just look at the code and look at the branches and be like, oh, here's how it does grammar parsing. Here's how it does recognition of various symbols. Here's how it does.
I'm sorry, I'm going to push back on that. You're going to change the interpretability problem. You're going to make some aspects of it better and other aspects worse. And I'm looking forward to the rest of the slide so that we can go ahead and give it a fair and honest criticism of the presentation.
This is all like future maybe. That's like, I hope this language will be, but it's not quite there yet. Okay. So how do you I already went over this. Parsers are functions. The one thing about this language that's, I think, unique from most other languages you may have seen is that the type system is also a function. Instead of having the type system be this kind of external program running in compiler, the type system can be defined directly in the language itself as a self-reflective program. Similar you could do in Lisp, but I don't think people have done this in Lisp as well as I think it can be done. And that's what I'm going to be walking through today. REPLs, they're also functions. So the basis of the language is something called the tree calculus, and it's these 3, 7-ish rules that basically allow you to re-implement the lambda calculus without binders. So you don't have to use, you don't have to implement fancy de-Bruijn indices systems. And actually, here's the point where I want people who have laptops to bring out their laptops and follow along. And come to this cool website here, which I made for the language. And take a look at, hold on. This cool thing.
Sorry, what's your click to get there?
It's displang.net, disp-lang.net.
Oh, this is the hello disp example on the front page.
Yes. And you can expand it, although you have to go into coding mode to expand it first.
DISP-lang for those of us who don't have good vision, right? Mm-hmm. Thank you. .net.
And so basically this is a kind of neat little thing that'll walk you through the evaluation rules of the tree calculus. We have the seven evaluation rules here. To create a stem, create a fork. This is the K combinator from SKI calculus, which basically all it does is it has this stored X and it ignores the past argument and collapses to that. The S combinator duplicates. Oops. Has two functions, reduces to a form where it applies the functions to itself, and that is how you duplicate things. And then the most important part is the triage rule, and this is what allows you to do self-reflection. This is what makes it different from basically any other combinator calculi you may have seen. If you have this form of tree, distinguished from that form of tree and that form of tree, and when you apply to something, it'll, depending on what you apply it to, if it's a leaf, it'll reduce to A, it'll reduce to that first thing. If it's a stem, it'll reduce to the second thing applied to what was passed. And that will be further application. You can see the little orange thing down there. If you apply it to a fork, you will get that. 2 applications.
Is there a pithy name for this evaluation rule out of the 7?
It's called triage, because you're triaging on the 3 forms that a tree can be.
I'm hoping spelled T-R-I-A-G-E, right?
Yes, absolutely.
Very good. And all these things that we are operating on are actually trees. If we needed to replicate an argument, we wouldn't have a partial order where some argument gets duplicated and put in, you have to copy it manually and create the tree so that you've got leaf or terminal nodes. Is that correct?
I believe so. There's nothing in this language besides, I guess, technically ternary trees here, because not everything has to be a binary relation. So some things you can implement in this. You can implement Boolean logic, of course. Does anyone want to guess what when I reduce this will happen?
You'll have a lot of raking to do.
Yes, but the trees and the leaves in the animation automatically disappear when they hit the ground.
Oh, I see. So you have a robot raker. Okay.
Yeah. See, they fade away.
All right.
Algorithmic botany with this?
What?
Algorithmic botany?
Yeah. So the F denoted there, that's the triage rule. And we're applying a stem, which will mean we'll get the first thing applied here. If you remember from over here, you're going to get the A branch. So when you have this, we'll get the A branch. And that is the representation of false in this language. False is just a tree with a single stem. You can do and false true. This big section is and. This is false. This is true.
Okay.
Does anyone want to guess what's going to happen when the first reduction here?
Well,
Which two trees will
survive?
will join together, and which ones will die?
So if F takes the leftmost one, then I assume that the one or two joined tree on the far left will make an appearance and somehow be combined with the true operator, true representation there.
This
However,
is the false.
And false true, so I'm not quite sure what that is if F represents the triage operator from before.
Right. So this whole tree right here, rid of this node is and.
Okay.
We've applied it to false, which is this tree right here, and then applied it again to true. And now we can see how the reduction goes step by step.
And by Boolean logic, it should come out to be false.
Yes, but how?
So what operator gets applied what? So what's the first thing that happens?
So the first thing is the triage rule, which is this F.
Okay.
Maybe I should have called it T.
So in this diagram, is any instance of a triage rule happening, does that just automatically cause an F to appear, or is that F special in some way?
So the F, so the special things are these little orange dots. The orange dots denote applications, which are distinct from,
And you put them there.
Yes.
They didn't appear from some other process.
And they're distinct from these roots. So this is a tree.
Yeah.
This is an application, which is not a tree. It is like a special its own thing. And actually, you can see that here, where so the rule we're talking about here is this. These are the trees. The application is like a special thing that may, in fact, create more applications to do recursively, but is not like a data structure. It is a recursive call.
Rigid trees, right? So in the example 3a, interchanging x and w is not allowed. That would be something completely different.
Exactly. Yes.
Okay. I did a theory on this 30 years ago.
So in this diagram, you said there are applications and there's triage rule.
Yep.
Add, I assume, is the application.
So add is the application.
Which one is the triage rule?
The triage rule is 3A, 3B, and 3C, the three variation of the triage rule. When you have this form of tree of W, X, and Y, depending on what you apply it to, whether it's a leaf, stem, or fork, you will get W, X applied to the stem internals, or Y applied to these two things.
But how did you denote, how did you differentiate the triage from the regular application?
Triage is just
F in the other one.
triage is just an application
It's just an application with a special
tree structure.
I see.
So
It's by the structure. There's no special symbol.
yes, the application, the symbol is just there for convenience of like, this is the rule it's about to fire, but like, it's just an application.
I see, because you said the tree itself is no longer binary. Is it, or is always binary?
What determines whether the F is there or not is whether or not this tree has a certain branching structure.
I see.
So it has to have this fork, yeah. And that's how application actually determines what to do. It looks at the left-hand side tree. If it sees a leaf, it does this. If it sees a stem, it does this. If it sees a fork, it does this. If it sees a fork with a stem, it does that. If it sees a fork,
There's an ambiguous application.
Yes.
It's more complicated.
I
Lack of
hope you
calculus.
flipped all of those diagrams 180 degrees, because you have to be very good shape rotators to.
yeah.
You just tilt your.
Or you can tilt your head.
Yes.
Well, then it'll be.
One other thing, just to stick with this for a little bit longer, this ad essentially represents the same object, application, functional, what have you, that operates on trees. At will return, in all these cases, the appropriate thing if it finds the appropriate thing on the input, in cases 0A through 3C. Is that, so can I assume that at is essentially the same thing in all these occurrences on this slide?
Basically, you can imagine this as like a rewriting system of like, if you see this subtree,
Right.
do this reduction, create these ats or these new things, yeah.
Okay. And in many cases, it's a reduction, but in the case of 2, it's a complication.
Yes.
Okay, because you need to decline, I guess, at some point.
You need
3C is a little bit of a complication too.
exactly.
Which is the S combinator. One is K, right? But 3 are the fancy ones that it has.
Okay.
Yeah. So this on its own is Turing complete.
Okay.
This is what makes it reflective
Okay.
or homo-iconic as
Why
the
was Turing complete not enough? It's pretty powerful.
because you can't in the same language you need a meta language to be able to talk about the code itself, talk about the machine itself.
Talk about it concisely and conveniently.
Yes. Now you could have quote and eval in your language, which is what Lisp does, but as Lisp I don't think has had like a good type system as far as I'm aware. It's kind of hard to do that kind of thing with quote and eval. This is a basically single thing quote eval, single rule quote eval. So back to this example. Since we have a stem here, we're going to take this branch. This is the leaf branch, this is the stem branch, this is the fork branch. And that's going to apply like that. And now we recognize that this has a K structure. So that's going to, so this is a stem, and so it's going to take this.
That's like K because it's like iconic to the SKI.
Yes. K as in ignores its argument and returns what's stored here. And now we have K again. Ignore its argument, returns stored here, and we get false.
What is it that determines that K is generated as opposed to some other operator there?
The definition of and.
Okay.
So if we just look at and on its own, this is a thing, this is a triage, because it has this double forking thing. Or this is a triad operation not yet applied to anything.
Okay.
And so if it's applied to anything, it'll first, if it's a leaf, or if it's a fork, it'll do nothing because it's not expecting forks. Booleans are only leaves or stems. If it's a leaf, it'll do, I guess you can try this. It's a leaf, it'll do that.
Okay.
Which I believe is, be applied to something else. Oh, that's S, okay. So basically it's going to, this is a encoding of the identity combinator in terms of S and K, where it ultimately works out to returning whatever's passed to it.
Okay.
So if it's passed a leaf, it'll return the leaf. If it's passed a stem, it'll return a stem. If it's passed itself, I think it'll return itself. Yeah, it'll return itself. Welcome to
So we have a pseudo-organic representation of Polish logical operators, I like to call them, because it was something that I just briefly encountered in Berkeley. I didn't really study the subject. So, thank you for the pretty pictures. What do we do with this?
we can do more things.
Okay.
Hold on. Do I have? Oh, I got. Okay. No, I still have this. We can do addition.
Yes, but what does it mean? We managed to what? Add up 5 things to get 6, or what?
Add 2 and 3 to get 5.
Okay.
So is that why they say 5 leads and then the grayed out one?
Yep. So this, or so this is 0. This is 1. This is 2. This is 3. This is 4. This is 5, and they're defining recursively.
So we found a cool way to increase the computational complexity of addition.
Yep.
Oh, wow. Okay. Now what?
Now.
In general, in this calculus, can you say that like if there's a tree with one child, that one child is kind of a constant because nothing will ever evaluate that, and that's what's going on here. Like the root that has like one.
Yes, this is a constant. So this whole thing is a constant.
Okay.
If there's no like application nodes,
It's awkward that you can like render this either up or down because it makes talking about the left or right child awkward.
I think there's still. Hold on. Do I have a way to? I can untreeify it. I don't have a way to flip it upside down yet. But it should just be like, just imagine dragging the nodes. Like that.
It's a classic problem.
Just like visualize it flipping in your head.
Can we multiply 5 by 7 without blowing out the graphics processor?
I don't have multiplication here, I don't think.
Oh, okay.
Can you define multiplication
version.
quickly?
You can define multiplication. Not in this thing. In the next thing.
No, yeah.
Okay.
Although I don't know it off the top of my head. All right. So you guys are familiar with tree calculus now. Wonderful. Now here's the programming language.
Okay. I'm hoping most of these are comments.
Yes, these are all comments, and we were doing live coding.
Okay.
So this is the language I've built. Basically, it's like kind of like Rust-ish, Rust flavored. Let thing equals 3. You can do reduction.
Is that a single equal sign?
I think it has ligatures enabled. Yeah, single equal sign. And then you can of course see that in the in the tree view. I can. Why is that? Huh.
Can we have thing 1 and thing 2?
We can have thing 2.
Dr. Seuss reference.
Thing is 3, thing 2 is 4. All right, so I'm going to define the basic operations here. You also have lambdas. So triage is this. And I can convince you this reduces to what we're familiar with. I guess, well, not, hold on. Did I do this correctly? I did this correctly. Oh wait, no, this is not triage, because triage is when you call it. So I think thing 2. I guess we can test it. Test triage. Unleaf, do this.
So syntactically, this is like one let statement defining several variables at once, it looks like.
This is like a case statement on trees.
But I mean, the fact that you only type the word let once on line 13.
So regular things are like public to the module. Let is private to the module.
Okay.
I'll just copy some things over, because why not? So yeah, you can just define things in this language. The I combinator basically returns back what it's passed. You can also define things with brackets or with a regular function notation.
What is T? You said that there's only one application.
Oh, sorry, T is leaf.
Ah.
So K is just leaf applied to leaf, which is this part of the stem. And when you apply to things, it builds up this little thing. Or I guess that's S, sorry. You apply to things, it builds up the fork, and then it builds up the application.
You get the light path up here? The visualization up here?
You click on the little tree icon next to it.
Oh,
I wonder why it's like small. It shouldn't be so small. It should be like raised up. I might go to. This might be better. Hold on.
what do the brackets mean?
So the brackets are basically, since this language doesn't have binders, if you want to represent regular functions, you need to somehow emulate what binders do in terms of like, basically the way I think about it, actually, I have a slide for this. Basically the way this works is you are taking a term that has a variable and trying to build like a sequence of S and Ks that'll take the variable, take whatever's passed, take whatever applied at the top level, and move it down the expression to apply it to where the variable is applied to. So yeah, this is a little AI generated, but so if you have some expression M.
I thought you were using combinatorial calculus to get away from binders. That's how you added them back.
Because they're nice to write with.
Yeah.
But ultimately they compile down to like this K2, X to Y to X compiles down to precisely the same thing that K compiles down to. And you can like say K equals K, I think. I think it doesn't like this. Wait, what? Oh, let me just comment that real quick. Resolve variable. Oh, right, I didn't define true and false yet. All right. What do you mean duplicate explorer? This is not what happened before. Anyway.
It sure looks like you're saying two trues make a false.
So this should resolve to true.
Except that T is a leaf.
It's application.
Mm-hmm.
It does not resolve.
So you can also do recursion. Oh, there we go. That's much nicer. Oh, that's why it's not working. I had everything defined down here. I'm just going to restart the page. So recursion, you need something called a wait, which is kind of like suspended application. It takes a function takes an argument and takes an argument and then waits for the third argument. Doesn't immediately reduce. Waits for the third argument because tree calculus is like by default eagerly reducing before it does the full application.
Can that be implemented without a runtime, basically? Can that be implemented purely in terms of the other basic tree calculus operators?
Yeah, basically what you're doing is you're creating like a miniature tuple or pair.
When you say wait, you don't mean like temporarily wait for time. You just
No, wait for another argument. Yeah. And you need that to define the fixed point operator, because it kind of like keeps your partial application of the continuation you're passing through to apply it when the current one is finished. And you can use it to define addition and do cool things like that. Thing for, just want to see this real quick. Huh? That should show the reduction steps, but I guess it's not. Okay, so that's need for later. The base of the language is types as predicates. Basically, there are no, like type annotations are basically just syntax sugar for insert a test that takes the type annotation and passes the term you parsed to it. So bool is literally just triage, take a term. If it's a leaf, it's a bool, because a leaf is true. If it's a stem, check if the stem subset is a leaf. If so, it's a bool, return true. Otherwise, false.
Actual false or actual it's not a bool type?
It's not a bool type.
Okay.
So types are specific. Types are basically just functions you run in code that return true or false. Yeah.
but they have to run prior to it. Like you want to type check statically still, right? It's a little different. Like you want to run the type checking without running the code.
So basically, you can do that by we'll define a new true function. If you give it bool type, that'll type check. Because basically, what it's doing is it's expanding it out to it's just inserting it in line test, which in some sense intuitively makes sense because like type checking is essentially a test that the compiler is doing on your code. In this, it's just like much more explicit of like, this is a test. And you can see all these tests pass, so it'll do true on true, it'll do true on false. It'll also do true on 0, because 0 is actually just leaf. So types in this language may like accept the members of other types, which is sometimes interesting.
Can you show us an example of a test that fails?
Yes. So if you try to do it on here.
Yeah.
Here we have a fork, bool type on fork. We expand bool type. That'll reduce to this, which will reduce to false.
Then why does it have a check mark there?
Because we're asserting it's false.
Okay. So in what sense is this test a failure?
If we assert it true, it'd be a failure.
There's an example that I can understand.
Sorry.
Thank you.
I'm in the mode of vibe coding where like the LM wants to assert everything is false even though it's or everything passes even if it's like a supposed to fail test. Another way to define the bool type is strictly by like if you define a thing that can compare arbitrary trees, you can just do tree equal true, tree equals false, which is a much nicer to read type definition, I think. And that does the same kind of thing.
You have a motto, types are predicates, not brands. Could you expand on that for those of us who aren't used to thinking of brands?
I'm not actually sure what a brand is, so this was
Your comment? Or
that is not my comment.
Oh, if it's not your comment, then I won't hold you to it as much.
So one of the things I want to be able to do with this language, one of future things, is so we have these two Boolean types. Tree equal is this really complicated fixed point definition. This really crazy tree. And ideally we'd be able to like prove somehow that this nice to read definition is equivalent to this kind of hard to grok one. That's my ultimate goal with this type system. I am not there yet. I'm still working on that. But anyone
Equivalent in what sense?
equivalent in that for all possible input trees, if one Boolean says some output, the other Boolean should also say that output. Should also give true or false.
So do you have an inductive type step for which you can show the equivalence for the smaller pieces and then the equivalence for the operator applied to those pieces in both cases?
I'll get to that next.
Okay.
So, sorry, by inductive step, what do you mean exactly?
So you want this to be true for all trees.
Yes.
This equals that when you apply the same tree to it. Well, if it's an empty tree, hopefully you've got a simple job there. If it's a tree with one node, hopefully the job's not too much harder. If you have a branch, then hopefully things are arranged so that the operator applied to the branch is, or excuse me, operator applied to the tree is some nice language construct applied to each branch, and that hopefully that can be mirrored in the other operator that you do for that. And then you can go ahead and say, since by recursion or induction or what have you, since all of the branches, both of these operators behave the same way on both of the branches, and since the trees are constructed the same way, I should get the same output for the larger tree.
Is what you're describing normalization by evaluation?
It could be, except I don't really know the term normalization or the term evaluation in this context. All I know is that, hey, trees can be built up inductively, and if I have nice enough operators, I can prove theorems about them.
So that's basically what we're going through next. Like, how do you, like it's easy enough to have a types as predicates, but what happens if you need to type functions? Okay, so I'm going to skip past this a little bit. This is just the nat type, which you can define via a fixed point. So like a trivial way to do this would be maybe you could define an arrow type that you want to prove that something's a function from A to B, and you need to somehow prove that for all possible inputs A, when you run the function on a given A input, it should always produce something of type B. And one way you might be able to do this is like enumerate all the trees, check if a tree is A, and if that on that same input you apply the F to the input and then it's B, basically, if that's never the case, return false. Otherwise, you have a function of type A to B. That's not going to work because we need to enumerate over all trees. Even if you had something that can enumerate over all of A, that would still only work for types of like finite elements, which
Types,
you need
that
induction
are
for.
populated only by a finite number of elements.
Yes.
Okay.
So essentially, what we do here, is make up like a special input called a hypothesis.
Okay.
And the way it's done in DISP is we have some special tag. We associate with it. What am I doing? What is going on here? I'm going to reload the page. We associate it with the type that we want to pass in, that we're trying to parameterize over. And then we have basically this as, oh, now the type can just be defined as make a hypothesis of type A, apply B to the hypothesis, and then check the output as B. This only works if you have, I mean, it works in trivial cases. So it works if it ignores their inputs, which is not great.
But does have application. It does have application. You have constant functions in
Yes.
general algebra, for example.
That is true. If you want to, you somehow need F to be made of some kind of set of operations that are like well-defined and nice. So we can do a little bit better if we have, let's say, the identity function by saying, oh, this is just going to return the hypothesis out. What if we modified the Boolean type to first check for our hypothesis? And if it finds a hypothesis of type bool, it just says yes. Otherwise, it does the concrete check. This is what hrap does, or the H rule. Basically checks if the passed thing is a hypothesis. If not, runs the type. If it's hypothesis, checks if the stored type is the passed type. Else, run the type regularly. And this is a little. I'm not actually sure the weight is needed there. But, wait, it is, yeah. Because you need to, because the stored type is the wrap type. So you need to take the type, take the wrap, check if the stored type in the hypothesis is equal to the wrapped type, where the body is the type. And then you have this new type constructor that you wrap all your predicate types in. And there you go. You have this new bool type that acts regularly, but also can do identity checking.
And is this successful because the definitions behind them are intrinsically finite, that if I unwrapped everything, it would amount to perhaps a large but still doable number of cases, or does this work because of something about operators that I don't know?
Could you elaborate more on that?
So we need to somehow make sure that all types check for hypothesis first before checking concretely. So that's nice. Let's suppose that we have the hypothesis. If we don't, then we'll make one. But if we do have the hypothesis, what does the hypothesis guarantee? That everything that was simpler passes the check? Or is the hypothesis something else that allows for this mechanism of validating that one type behaves like another?
So currently, hypothesis is just like a little tree that stores the type, and that we can use to basically, if we get a resulting hypothesis out of some function application to a hypothesis, we assume that whatever was done in the function, the output hypothesis is the result of the function.
Okay.
We assume it translates over to concrete applications.
And on a higher level or metal level, if we get a hypothesis out, then something is working and we can continue on our merry way.
Yes.
Okay.
So basically, the whole name of the game here is how do you, in some sense, restrict the space of functions from arbitrary trees to things where you can pass hypothesis to it and get hypothesis out, while it also still doubles as something that can take concrete values and pass concrete values out.
Oh, so if I have a particular description of a function and hrap is applied to it but somehow fails, then I don't have a proof of f, but then hopefully that shows up. And for those functions f whose descriptions do admit this, then I can make a proof.
Yes.
Okay, that makes sense to me. So if we had something here that says, so this will work for certain kinds of functions, but maybe that's the next part of the slide.
Yes.
Okay.
And it's not precisely a proof. It is you will have a predicate that you can call the function with, and if it returns true, then you know the predicate, you know the type holds.
Okay.
So with type checking then evaluates the function. It's not a syntactic thing on the tree. You just walk and analyze it. You literally run it through the evaluation.
It is normalization by evaluation, where the actual function you call normally on concrete values and the function doubles as the function you can call an hypotheses to get hypotheses
It has a
values.
side effect. You would observe it, but of course there's no side effect.
Well, there actually are side effects in this language eventually, but that's a
Usually
future
don't want
feature.
side effects while type checking.
Yeah, not while type checking. Side effects are monads you build up to pass to some external evaluator. same Haskell. All right, so this is about as far as I got in terms of the walkthrough. There is more walkthrough that goes more into how do you actually precisely characterize the space of functions that you can type check.
This is not your walkthrough. This is someone else's walkthrough.
This is the rest of it's a bit AI generated.
Oh, so this is a walkthrough that you inspired, but someone else wrote or something else wrote.
Yes.
Okay.
Um,
Dun, dun, dun.
So would you say this type system has dependent types as in Lean?
the full type system is dependently typed.
Is dependently typed.
And actually can support something a bit more general than dependent types, dependent contexts, which I guess you can technically define in terms of pi types, but
So earlier you had a fixed combinator in lambda calculus. It's not possible to type, right?
right. So for the fixed points, kind of the current state of that is just like, if type checking terminates, then it's as a type. But if either the function application to the hypothesis somehow doesn't terminate, or the type checking itself, checker itself sometimes doesn't terminate, then you just like assume it's not typable, or you assume it's like some paradox or something. That's how I get around not having universe hierarchies. Although you can actually write in this language this, which is kind of cool. But that's maybe for another time. So okay. So we have this simple hypothesis thing. We can type check the identity function. Ideally, we'd like to somehow type check bools that you can easily figure out a way around this. Just use triage. Triage is one of the main issues. There's three main issues. If you can triage on hypothesis, you can do one thing if hypothesis is passed, something else if not. And so you kind of broken your guarantee. This might be a little involved. maybe I'll wrap it here.
So you can wrap the description of the language here, but I'm hoping that you'll actually say, even though this is in the works, this is my plan for how we're going to be able to transpile, or this is my plan for how we're going to be able to handle these language features, or this is my plan for, this is what types of language features we're going to ignore when we go ahead and translate from one to the other.
So, yes. I've kind of been inspired by Lisp macros. I'm imagining a programming language where you can literally just, the parser itself is a item in scope you can modify, and it changes what's parsed later down the file. And so if you want to recreate another language, you essentially just redefine the parser object, redefine maybe the elaborator object, and that would allow you to write the syntax and write the semantics in another language. When it comes to translation, though, that's much more, you need to basically do some prove some equivalences. You need to define some translation from, let's say, Rust to Disp, where given some evaluator Rust, given some evaluator Disp, the Rust code and Disp code, when going through the translation, will respect functoriality of, you evaluate both of them, they both get the same output. I don't have anything beyond, if you have a powerful enough type system and you can do this kind of define language in a language type macro thing, maybe you can do something fancy like, I'm going to define this header file which implements the Rust programming language syntax and semantics, translated all the Disp semantics such that evaluation is the same, given some model of the Rust compiler, or possibly just the Rust compiler itself, if it eventually gets sufficient enough to do that, and then be able to just like take all the Rust code you want, plop it in the file, and have it run as Disp. And all you do is write a thing that goes back and forth. What was another question you had?
I actually have a bunch of questions, but the one that's forefront in my mind is, have you studied homomorphic compilation?
Homomorphic compilation. That feels like something I would have seen, because those are all words I kind of know, but I'm not sure precisely.
So I saw this several years ago, so I probably have the details wrong, and there's probably a better term I should be using other than homomorphic compilation, but the idea was that you had a language that you were going to compile to, and sorry, I'm a dinosaur here, we're interested in actually ending up with a binary or running it on some processor so that we can do stuff. But the idea was that you had a representation of a language and you were able to get a homomorphism of various algebraic constructs that represented things in the language to something a little bit simpler that you could run, I don't know, a checker on, or a code generator, or an optimizer, or what have you. But also another application of this, which I thought was really interesting, was that if you're able to do it in the right way, and I might actually be confusing things here, but I think it all ties together, you would be able to homomorphically encrypt computations so that you could take the result of your compiler, run it on some public server, and the server has access to the execution trace and everything, but it couldn't tell what you were doing because the computation itself, the function itself, was encrypted, and the outputs would be encrypted too, so you could do certain kinds of authentication or what have you with a higher degree of security than before.
Or things like you have this compiler on the server and someone wants to compile their code, but they don't have their own servers and they don't want to make their code public to the server. You can have the compiler be done homomorphically. I'm not sure those are related. I think homomorphic encryption might be something different, but I think they share the same kind of algebraic root.
Right, and because of your idea of putting a wrap around these things so that you could try to show that certain functions were definable or so that you could do type checking, it sounds like you could do something similar here. And there is such a thing, I believe, as homomorphic compilation, which may not be exactly the same thing, but it's something that you might be interested in referring to.
I'm definitely interested in homomorphic encryption. My current understanding is that like it's way too slow and unpractical because like the optimizers and compilers aren't quite there for it. Once they do, that'll be like a huge thing most likely.
Okay, but one of the things I believe this presupposes, and I'm sorry I can't bring a reference to mind for you to look at, it presupposes that you have something and something. And the thing I think the something is an algebraic model that represents the semantics of the program to go ahead and actually operate on and try to do things so that you can do appropriate and correct compilation and perhaps even fast compilation. So I'm sorry, I should have something better than 2 words to give you, but I think if you dig a little bit deeper, you'll find the paper I'm actually thinking of. And unfortunately, I can't remember a word of the title of the paper.
I will definitely keep that in mind.
Okay, so that was one question I had. A second question I had was...
Do you have a question?
Oh, yeah.
Yeah, you might have. So I just want to ask, what is it about the tree calculus that makes it decentralized, or enables decentralized stuff?
So I'm not actually sure if there's actually that much special tree calculus over something like Lisp, where you can also do this kind of like self-reflection. I think the main advantage of the tree calculus is just its simplicity. Like everything's just a tree. You don't need quote eval. And I think my favorite thing is I can implement normalization by evaluation without having to deal with De Bruijn indices, without having to deal with binders, without having to deal with like having this meta language that has neutrals in every type and like.
So you're saying like a simple core.
A really simple core.
There's nothing special about this core.
Simple core, clean backend that he can go ahead and do a lot of these manipulations, because once he's able to take whatever his language is into this set of tree structures, then he's got a bunch of very simple and powerful tools to work with to do the kinds of transformations he's interested in.
Full disclosure, most of this project AI generated, I'm going to be honest. But just the core of what you need to do normalization by evaluation is under 250 lines. Compared to the lean kernel.
I'm sorry, could you say that more slowly? Under
250 lines of code.
Under 250 lines.
This file right here is basically
is the core.
It is the core. It's actually more than you need because they have all these comments and these unnecessary things. That this verifies a module. The only thing you really need is this param apply operation, which takes a type, takes a term, and does simulated reduction, forbidding certain kinds of applications or certain kinds of operations. For example, any operation that would inspect a hypothesis or a neutral, any operation that would triage has to be forbidden or checked. Also, you need certain primitives to allow you to actually mint hypotheses if you're defining types in terms of this. But that's all you need. You just need some kind of evaluator you can define in the tree calculus that simulates regular tree calculus reduction, but forbids certain operations to do normalization by evaluation, to do type checking. And that is all the type checker does.
Do you have any examples, simple or partial, where you are using this to translate? I would like awk, of course, but some people might prefer brain F star CK translated to Turing machine language or something like that. Do you have any examples of that kind for public viewing?
Not yet. This website I made literally in the last week.
Of course. In theory, or do you see coming within the next week or two, say, here's my version of Pascal translated to awk, or here's my version of Fortran translated to Turing machines, or here's my example of brain F star CK translated to something?
So I'm actively working on that. That is like, well, currently I'm working on like a faster way to evaluate these things. So this is something called, anyone here familiar with interaction combinators or interaction nets?
No. You might be, but I'm not.
So these are kind of cool graph reduction machines that basically allow you to, in parallel, do reduction. And this is a version of interaction combinators built on a cellular automata lattice. So every operation is done locally, including the wire reconfiguring and movement. And basically the use layer, maybe I can make reduction go on a GPU really fast. Yeah.
Can you talk about like what kind of closure you have for that?
What kind of closure?
Yeah.
Or?
So like, how do you keep it from blowing up?
Oh, you don't. If a term blows up, it blows up. It's just a matter of
Do you have any
can your type system sufficiently restrict the space of programs to programs that you can check ahead of time, that sufficiently useful programs that you know won't iterate forever, or will always terminate for any input, even inputs of like cardinality n types.
Regarding interaction combinators, I don't know much about it, but what I've read is, there's something about that calculus that enables you to, run massively parallel computations across a bunch of machines or something like that, right?
Mm-hmm.
Does the tree calculus have similar properties? Or I guess in general, what's the relationship between them?
So the goal is make tree calculus like similar languages like Bend that can run directly on GPU and compile to various backends. But even more so, once the tree calculus has advanced enough type system to be able to prove things like equality of different implementations, and this could include, for example, an implementation of assembly calculus, or not assembly, assembly reduction or evaluation in the tree calculus, like an emulator of x86 or something. If you can prove that some assembly program under this emulator is equivalent, because they're all just tree calculus terms, to some nice tree calculus high-level written term that's really slow to evaluate, but is nice to read, you could use that rewrite in a kind of optimizer that would allow you to automatically prove rewrite rules for optimizers that can compile down to assembly, and you can get assembly programs. The goal is to get assembly programs out of this, or possibly like combination JIT assembly programs that can like spot-wise optimize things. Yeah.
Back to the interaction nets thing. I've seen that they have been used as like a sort of operational semantics of like linear logic, and I know linear logic can be viewed as like a process calculus.
Mm-hmm.
I don't know much about interaction nets, so like what makes it useful for that like parallel computation thing?
Not sure how good of an answer I can give here beyond when you have things like the S combinator. Which I believe, S fork, I think that's the S combinator, right? maybe not. I don't know. When you think like the S combinator, where you're duplicating like the past variable x, with interaction nets, there are terms you can use to like make sure you're using the same x variable and you do it lazily. So if like one branch of computation gets cut off, you don't have to evaluate that. I'm still working on this. I don't understand interaction commutators very well. I drew up on a whiteboard somewhere all the different agents.
Why did you choose the tree calculus for the core of your language? Like, is this something you're now,
This is still a tree calculus.
Oh, it's still a tree calculus.
Yes.
So this interaction nets is not alternative to a tree calculus.
It's just a backend evaluator.
I see.
You need so like here's leaf, here's stem. This n is like a normalization agent that like tries to take a tree and reduce it. The A's are other things. This is 3D, by the way.
This is a mechanism to give you perspective on how these combinators work with each other and allow you to consider possible optimizations or rewrites that would be beneficial to your design of disk.
Yeah, like maximally parallelize and like get a fast enough disk evaluator that you can like parallelize.
Not
Sorry.
paralyze. That's
sorry. Maximally parallelize. Parallelize.
Do it slowly so that people don't misunderstand.
All right. Evaluation. So you have like a something you can build off of when you're trying to prove equivalencies of large proofs and things like that. But ideally, you will have this kind of reduction that runs an optimizer that tries to optimize itself into assembly code or something.
Do you have any toy examples where you can take an implementation that has however many of your combinators here and actually push them onto a GPU so that the GPUs can each run one combinator or something like that? And
this is that actively being researched. So this is a cellular automaton.
Right.
It might be hard to see, but these wires are going into the third dimension. Okay. This is basically a 3D matrix of state. I think each cell is like maybe 4 bits, or sorry, 4 bytes.
This is a representation of a program that you are running, and the wires actually represent some kind of virtual connections between different processors, each one of which is implementing a particular combinator.
This is a cellular automaton.
That.
Each cell can either be a wire or an agent.
Okay.
And it, through local rewrite rules, it can bring agents to each other to reduce them, emulating the tree calculus.
Okay, so it's a cellular automaton that's reevaluating an expression in the tree calculus or the operator calculus to provide something that may be a better representation for you.
Faster to evaluate. It's the same, better representation, and that's faster to evaluate. Yeah.
Okay. One that's your favorite. One that you like more.
It looks cool. It looks really cool.
It looks cool. And of course you have your favorites, but you might also want to.
I think that the goal is targeting GPUs.
Yeah. So this is like it's gonna be running like a fragment shader kind of thing.
Cool. Let's thank the speaker.
Okay.
Thank you.
Final question.